and we're going to talk about problem 3. An undirected graph is said to be bipartite if all of its vertices can be divided into two disjoint sets, u and v, such that every edge connects an item in u to an item in v. I think a more simple way of saying this is basically that your graph can be made every other. In other words, if u is in set, or if this node is in set u, every other node should be in set u, and all the ones in between should be v. And so in these examples, the graph on the left is bipartite, right? Because you can say we can color the graph in an every other fashion. But for this graph on the right, we can't, right? If we said this node was in set u, well then this is not every other because we're connecting two things in set u. Or in other words, this edge is breaking this rule that it connects an item to u and item in v. And if we were to say this node was in v, well then that violates it here, right? Because we're connecting a v to a v. And so this graph can't be colored every other, or it's not bipartite. So can we provide an algorithm which determines whether or not a graph is bipartite? And what's the runtime of this algorithm? Our hint is to modify an algorithm we already know. So take a moment and think about this one because it's a pretty interesting question. So here's my thought. We basically know that we want to start somewhere and say, okay, can we color every single or every other node in this graph one color and then all the other ones the other color, right? So what if we just pick some starting point and say, okay, arbitrarily, you're in set U. Everything I'm connected to should be in set V. And everything those nodes are connected to should be in set U. And everything those are connected to should be in set V. And we're sort of doing this traversal of the graph, right? And we're coloring things or denoting which set they are in as we go along. And I want to emphasize the coloring is just another way of representing which set they're in. So we're traversing the graph, and every time we're at a node, we just want to make sure all of its neighbors can be made the other color. But if, let's say, at any point we said, okay, we're starting here, and we're going to make all of my neighbors blue or in set V, and then we'll, traverse the graph a little more, and we'll get here, and we'll realize, crap, all of my neighbors need to be in set U, but that conflicts with something I said earlier. Therefore, this graph is not bipartite. So now, taking all of this together, can we think of a real algorithm we could modify to do this? I think that using either BFS or DFS would work. As long as we have some sort of graph traversal algorithm we can use underlying, we just have to follow along that algorithm. And whenever we look at a neighbor, we're just going to denote it the opposite color of what I am, or in the opposite set. And if at any point I want to say that one of my neighbors belongs in the other set, yet that conflicts with something I said earlier, then the graph is not bipartite. On the other hand, if I can get through the whole graph and never have any conflicts, I can always successfully put my neighbors in the opposite set of me as I traverse the graph, then the graph is bipartite. So using BFS or DFS, and we're making this small modification just to check sets as we go along and associate each node to a set. So what is the runtime of our algorithm? Well, it's just the same as BFS and DFS, which means our runtime is O of V plus E. Super awesome. Now we're going to move on to part B. Consider the following implementation of DFS, which contains an error. Identify the bug and then give an example of a graph where this algorithm may not traverse in DFS order. I'll give you a moment to think about it. Now, my first hint to you is, when should we be marking vertices? That's a little hint for where the bug is. And so looking at this closer, we realize the problem is that we mark neighbors as soon as we put them onto the fringe. But a correct implementation only marks nodes when they've actually been visited. because the whole point of marking things is to say, hey, we visited this, right? That's what it means to mark a node. It shows that the node has been seen before. So if that's the bug, just to show you how we could fix it, we could just make sure we're going to mark the vertex as we pop it, not when we're pushing onto the fringe, but as we're popping it, as we're really visiting it. And we just want to make sure we're only doing this if the vertex was not already marked, so that we're not doing duplicates here, right? So that was the bug. Now let's give an example of a graph where this algorithm may not traverse in DFS order. So we're returning to that bug or that buggy implementation, and we want to show an example where the bug really reveals itself, right? So let's take a moment and think about this one. So we think about the fact the problem with our buggy implementation is that it marks things when we're adding them to the fringe or when we're like sort of peripherally viewing them as our neighbor. And then we say, okay, now we can't visit them again, or like we can't re-add them because we've already seen them before, when that's not true, right? And so we want to think of an example where we should be adding something to the fringe, yet we're not because we've seen it before as a neighbor. And so we can think of an example where you're starting it, let's say some node A, and you have some children B, C, and D, right? And let's say, so when you're at A, you're definitely going to be adding your children, all of them, to the queue or the fringe, right? Sorry, the stack, not a queue. DFS uses a stack. And so you add B, C, and D to the stack. And at this point, they are all marked because as we push our neighbors onto the fringe, we incorrectly mark them, which means that if we see any of these nodes again later, we're not going to correctly put them on the fringe as we should. And so why don't we just say, okay, how about we put B, C, and D onto the fringe and we like maybe break ties alphabetically so we see B first. And then let's say B has the child D, right? And so in a correct DFS implementation, D should get added to the fringe because you're going to want to have this BF depth first. Like we start at A, then we look at B, then we look at D because we're following the children deeper and deeper, right? But because our buggy implementation incorrectly says, oh, D has already been seen, it's already been marked, it's already on the fringe, we don't re-add it to the fringe, even though we have this edge from B to D. And so upon visiting B, we don't add D to the fringe, and we just move on to C, and then we visit D eventually. And so we get the order A, B, C, D, when the correct DFS order for this graph would have been starting at A, then adding B, C, and D to the fringe. But once we're at B, we continue digging deeper, and we'd visit D next. And so the correct order would have been A, B, D, C, because we always want to go deeper. And so this reveals the bug in our graph algorithm or our DFS implementation. Finally, for the last problem, since it's extra, I am actually not going to bother to explain it right now, but if you are really curious to see the walkthrough, you can go to Anjali's video, which I will link below, and she does a great job of explaining this extra problem. And that is this whole worksheet. So thank you for tuning in and have a great week.